So I'm going to use these couple of minutes to introduce our first speaker. Let me just point out a couple of things that you've already heard. One of them is that you can share in the conversation here on Slack. The Slack channel link has been added to the chat a few times. We'll add it throughout the day, so it's refreshed there. Also, we have a Twitter handle, so you can use hashtag Lisa Canada if you'd like to join in that conversation. As one of the organizers, I will just apologize in advance that because we're using Slack, you're going to be hearing this sonorous swoosh of Slack going on in the background whenever I'm talking to you all. So hopefully that will be pleasant and not annoying. So I'd really love to have you all join me in welcoming our first speaker of the morning. I'm going to take these 2 minutes before she starts just to give her an illustrious welcome, because then I don't cut into her time. So our first speaker of today is Kelly Holley-Bockelmann. Kelly, for those of you who don't know her, is the Stevenson Professor of Physics and Astronomy at Vanderbilt University. She's also co-director of a really fabulous program called the Fisk Vanderbilt Masters to PhD Bridge Program, which helps bring students in through the Fisk Masters program and transition them with a lot of really fantastic supports into the PhD program at Vanderbilt. Kelly's had a long relationship with the LISA mission. She's the chair of the NASA LISA study team and also a US representative to the LISA Consortium. If you go in and browse around in some of Kelly's fantastic research, you'll see that she's thought deeply about the theoretical underpinnings of what happens when supermassive black holes merge. And she brings a lot of joy and enthusiasm to this science case. She's just a fantastic speaker, and we're extraordinarily lucky to have Kelly here with us today to introduce LISA and give us an overview of the science goals of this really fantastic instrument that is well underway. And so hopefully everybody can join me in welcoming Kelly, and Kelly will ask you to share your screen and we can debug any issues about getting that set up. So welcome, Kelly. Hello. And please, everyone, just a reminder, please toss your questions into the chat during the talk or take them up on Slack. Do our best to bring those into the conversation toward the end. Kelly, take it away.
Hi, everyone. It's really nice to see y'all. I am going to help debug. Y'all can help me debug while I try and make this presentation reasonable. I'm going to switch. I'm going to go to the next slide, and about half the time that works, and about half the time I have to stop and share again. So I'm going to say, can you see me? Did I change slides? Okay. Oh, I'm seeing there's a little bit of things cut off, but that's just the first slide. Okay, so I think we're going to be okay. And if not, we'll work with this. Anyway, it's really great to see you all. I'm so glad to participate virtually with you all and share the love of LISA. So I just wanted to let y'all know in the 35-ish minutes of time that I've got with you, I'm going to tell you a little bit about LISA science, but we're not going to cover things in dramatic detail. And among the audience are the world's experts on the exact science that I'm going to be talking about. So please use the Slack and we can throw questions to those experts, and we'll get your questions answered. If not by me, then by other folks. So I'm super happy to have this time to chat with you. So first off, I'm going to take a step back. And I'm going to tell you about our friends photons. Those of you who are astronomers know and love photons, but I want to tell you, photons encode certain things about the universe, and they are excellent at encoding things like, the temperature of gas, the density of matter, the kinematics of matter, and even its composition. But the problem is that photons are very, very interactive with matter, and so therefore they're going to be distracted from the source to the observations by other matter, by magnetic fields, by other photons. And so you very rarely get a pure view of what is happening at the source. And you can see this with this gorgeous picture of Gaia. Those nice dust lanes in the plane of the Milky Way are blocking our view of some really excellent things happening. And as you all know, as soon as you look in a different regime of the electromagnetic spectrum, you get yet another point of view about the universe. So this is a gorgeous picture of the gamma ray sky, and you get to see an entirely different point of view. You may even notice some faint hints of the Fermi bubble here. You get to see highly interactive X-ray binaries, etc. And so now we're going to talk about gravitational waves because they encode different physics. So gravitational waves encode information about the changing of space-time. And what changes space-time is matter moving. And so you get information about the masses of matter that's moving, the spins of black holes and their directions, the particular orbit of that moving matter, and the distance. And I'm not talking about redshift, I'm talking about the proper distance. Just to give us an idea, here is a classic waveform of two black holes merging, and there's just some terminology I want y'all to recognize. There's the amplitude of this gravitational wave, and that scales with that distance that I was talking about. Sort of the intrinsic amplitude here encodes some combo of the mass. And the change in that, the waveform, this kind of increase in the frequency, that allows you to figure out what the individual masses are. So this combo of mass is called the chirp mass, and that's encoded here. And the chirp, or in other words, the sort of frequency increase, that encodes individual masses. So I'm going to show you what I mean by the fact that this encodes, gravitational waves encode different information. And I'm going to do it by sound. So hopefully you can hear and holler if you can't. First off, I'm going to show you the waveform of two equal mass black holes that aren't spinning on a perfectly circular orbit. I'm just going to play what the waveform is translated into sound. So you heard, hopefully, you heard sort of a low frequency. That was when the black holes were rather far apart, orbiting rather slowly, emitting gravitational waves, but relatively weakly compared to later on when they start to emit gravitational radiation that takes energy and angular momentum away from the orbit. The black holes get closer, they orbit faster, the frequency goes up, and then sort of towards the end, you hear that chirp. And that is when the black holes are so close that they lose enough energy per orbit to not be allowed to orbit, complete a full orbit before they get closer. Hopefully that makes sense. So that goes whoop, and then they merge. I'm checking to see if people heard. Oh, good. Phew. People heard it. Thank goodness. Okay, so now I'm going to change things, and I'm going to have these black holes have spin, still equal mass, still in a circular orbit. So that more complex pattern is the spins being projected onto our line of sight. So you see that beating pattern of the spin and orbit kind of coupling there. So you can see how easily that kind of information is directly encoded in the gravitational waves that we receive. And that gives us an entirely different view on the universe. And just backing up again, the things that make the strongest gravitational waves in the universe are going to be things that are that have a time-dependent quadrupole in the gravitational potential, aka things that aren't perfectly spherically symmetric, moving around pretty quickly. Great example are binary things like binary stars, binary black holes. They make enormous gravitational waves. They have a very strong quadrupole moment in the time-dependent gravitational potential. Anyway, one other thing I just wanted you to notice about this picture, unlike electromagnetic waves, which have this dipole radiation pattern, you see how these are clover leaves? That's a quadrupole radiation pattern. And just that's one difference between electromagnetic and gravitational waves. And that'll, you'll get a little bit of that difference when you talk about orbital frequency versus gravitational wave frequency. But just like an electromagnetic spectrum, there's a spectrum of gravitational waves, and y'all are very familiar with the beautiful work out of ground-based gravitational wave observatories that have opened up the universe in terms of binary black holes that are merging, neutron stars that are merging, and you know, just an enormous bit of universe that comes from the last sort of millisecond of merging matter. And so you can see here, this is like the gravitational wave spectrum. Here are pictures of the types of observatories. These are the time scales over which the objects are, you know, are changing their mass. So you're catching the last little millisecond of some process. And here are the types of sources that are expected in that wave band. And so we have met this part of the universe before, and it's fantastic. But I'm going to talk to you about these longer wavelength gravitational waves that are from LISA, from space-based observatories. And so think about things, matter, that orbits one another or changes dramatically on timescales of like minutes, so hours to seconds. And the gorgeous thing about this gravitational wave band is that there's a ton of known sources already in this region. And I'm just going to walk you through some of those. I am going to skip this fabulous movie that tells you all about the LISA instrument because you're going to get that in just a second. The only real thing I want to tell you as a theorist is that the reason why we're able to capture this longer gravitational wave part of the universe is because the detector arms are so large. And so these arms in LISA are 2.5 million kilometers separated. And so I always like to think about a detector being able to detect wavelengths that are, you know, sort of smaller, but not a ton smaller than the size of the arms. So think about it that way, or not. But anyway, this is a fabulous movie. Y'all should see the instrument. The other cool thing I like to talk about for the LISA instrument, which I said I wasn't going to talk about, but I'm so excited about it, I'm going to do it anyway, is when a gravitational wave flies by, you know, you get this kind of change in the space-time length between these vertices of the triangle. So you'll get a characteristic delay in the light travel time between the vertices. And the cool thing here is, you know, this instrument is on an orbit around the sun in the Earth's the same Earth distance as from the Earth to the sun, but it's far enough away so that you can basically fit all the planets between the arms. So anyway, that's kind of fun. I'm going to skip this one too, because you're going to hear about how fantastic the precursor instruments were at proving that LISA can do what it says it's going to do. But if you want more information, just holler. What I really want to talk to you about is the discovery space for LISA. So I'm going to spend a little bit of time walking you through this figure, and we'll keep coming back to it. So the vertical axis is basically the differential change in space-time, in the length of space-time. So it's like delta L or over L, or you could think about it as a differential time as well if you want. But anyway, differential length called characteristic strain as a function of frequency. And this little red line here describes what is called the sensitivity curve of LISA, and anything above this is going to be observable. And the neat thing about this figure is that it's color coded by the signal to noise ratio. So, you know, if you see something yellow like this, it's got signal to noise ratios of a couple hundred. Okay. And also noted on these figures are typical sources that you will see, we think, with LISA. So I want to draw your attention to the classic type of source that you'll see with LISA, and that is going to be two merging black holes, supermassive black holes, like the ones that are the one that is at the center of the galaxy, that's about this mass, orbiting around one another about, you know, like a month-ish before merger. And they're moving relativistically, crazy fast, and making enormous gravitational waves. So you'll see right before merger, they make very, very loud gravitational waves. In fact, some people think that these are the loudest gravitational wave sources in the universe, supermassive black hole mergers. And the interesting thing about this, these two equal mass black holes and their tracks in gravitational wave space, is that these are all calculated at redshift 3. Which for electromagnetic observers is pretty distant as far as resolving individual sources. So I'm gonna back up just 1 second and say, by the way, we for sure know that these black holes exist. Andrea Ghez and Reinhard Genzel's groups both won Nobel Prizes for showing that inside the Milky Way galaxy, there is a roughly 4 million solar mass black hole, and they determined that by individual stellar orbits. So we know these supermassive black holes exist, and we know they sit at the centers of galaxies. And in fact, kind of going further, we know that they exist in almost every galaxy. Not every galaxy, but almost. So for example, we're finding roughly million solar mass black holes in these galaxies that are called bulgeless galaxies. So they basically don't have a center, but they do have a black hole. We're finding, as y'all may know, really, really distant supermassive black holes that are, billions of solar masses early on in the universe. So this is a picture of, the Big Bang and time evolving. The black holes that I'm talking about that we're seeing are in our relatively local universe. We know for sure there are also ones that are much more massive early on in the universe. It's tougher to see the lower mass black holes early on in the universe because they're dim, but we think that they're there because science. Right, so we also are finding more and more smaller black holes, these million solar mass black holes, which, okay, they're not really small, but they're small compared to quasar billion solar mass black holes. So we're seeing these million solar mass black holes in little dwarf galaxies like this one, Henize 210. And so we're finding more and more a population of lower supermassive black holes. They're even in low surface brightness galaxies like Megalin 1. So you're finding them everywhere. And going down the mass spectrum, we think we're finding this class of objects called intermediate mass black holes, which here may be an example of one that's maybe 500 solar masses at least to a couple thousand solar masses, and it is sitting on the outskirts of a nice large galaxy that has its own supermassive black hole at the center. So in this region that Lisa will observe, there seems to be a wealth of these types of black holes. Oh, sorry, I'll skip that one. Just a heads up, we think galaxies evolved by merging together. Here's a lovely example of, let's just look at this part. Well, you can look at either one. This is the stellar portion of a simulation called Illustris that will eventually over time form something like a Milky Way mass galaxy. And here's sort of the gas that is involved in this. So you're only seeing the stars here and the gas here. The thing I want to draw your attention to is that it's like a mosh pit. There's a ton of merging hierarchically from smaller objects to form bigger objects. And look, if there's a black hole in each of the centers of those pieces, then the lifetime of a galaxy is also, synonymous with a bunch of black hole mergers. And each one of those black hole mergers, we think, emits a ton of gravitational waves. And, if they're in a certain mass region, they will be observable by LISA. So LISA's a great way to track in real time, well, okay, not real time, way to track the growth and assembly of structure in the universe. And this is that example. I love this figure. This is my favorite figure. So it is my drop the mic figure. I didn't make it, but man, it's awesome. This is redshift, okay, and sort of distance also on the vertical axis as a function of the total masses of the black holes involved in a merger. and sort of color these little markers here, talk about the regions of that mass distance space that can be probed by current observations, either electromagnetic or gravitational. So this is sort of LIGO, looks at lower mass black holes in the relatively local universe. And with electromagnetic surveys, we can get those quasars, right, at larger distances. But in the background here are these beautiful contours of this waterfall plot, and these are noted the signal to noise ratio at which you can observe that type of merger. So in other words, a 10 to the 6 solar mass merger of two black holes that make up 10 to the 6 solar masses can be seen with signal to noise ratio of 2000 out to redshift 4, which is astounding. And the best part here is this. Notice I've marked this region here called the cosmic dawn. ENM observers know that this is the kind of no man's land afterwards. There'll be dragons afterwards because the mean free path of photons is really small. So you cannot see anything in this region electromagnetically, basically, because the universe is optically thick, and you don't get another signal until the CMB at Z of 1100. So this marks roughly where we think that happens. And hey, guess what? You can observe Milky Way mass black holes merging at redshift like 20 with signal to noise ratios of a couple hundred. So done. If you want to think about supermassive black hole growth, its connection with galaxy growth, how supermassive black holes are born, etc., Lisa's your instrument. So yay. In fact, you can determine, or we think, you can determine the ways in which supermassive black hole seeds are sown in galaxies. I'll skip this slide because I want to get to other things. So yes, you can learn about the mergers of binary black holes in this regime. You can trace how they are combined with their host galaxies. You can complement X-ray surveys, which will probe a different channel, right? It'll probe not the merging black holes necessarily, it'll probe the black holes that are accreting a lot of matter and emitting X-rays. So you get that from ENM, and you'll get the ones that actually merge together and grow by mass assembly through mergers with gravitational waves, all the way out to ridiculous redshifts. Okay, so that's my personal favorite type of source. But hey, there's a ton of other sources with LISA. And so I love LISA because it touches almost every area of astronomy, including like space weather. But the next source, which is for sure going to be seen with LISA, are these millions of white dwarf neutron star, basically compact object remnants orbiting in our galaxy and in the nearby universe. So as soon as you turn on LISA, there will be the hum of roughly 10 to the 7 close white dwarf binaries all throughout the galaxy. And so much so that see these, this is almost a confusion foreground of all the white dwarf binaries that are on, they'll merge in a million years, but they're all humming at once. Oh gosh, here's mine. Sorry, gravitational waves are not affected by dust. Remember, it's space-time. So you're going to see all of them. And in fact, here's sort of a pretend view of what we think we're going to see gravitationally. Here's a little model of all the close white dwarf binaries in the Milky Way disk, some globular cluster modeling, the SMC, the LMC. And here's what we know. This is kind of old, but here's what we knew a couple years ago about the close binary systems in our galaxy through electromagnetic radiation. There's been a lot of work in this area, so this is very outdated. And in fact, the sensitivity curve is also outdated, but you get the point. There's a generous handful of ENM bright binary systems that we know of. We certainly can't see the other side of the galaxy, much less etc. But we'll see all of them with gravitational waves. And in fact, you can do some cool science that way. you would probably want to remove the foreground if you wanted to look at background stuff, but there's information in the foreground. Like, for example, if you looked at this picture in different frequency bands, gravitational frequency bands, you might understand something about the metallicity distribution of these close white dwarf binary systems, and so forth. So you can do some archaeology that way. And in fact, in this region, what we would love to do is map this old stellar population of the Milky Way, maybe even learn a little bit about galactic structure on the far side that we can't see electromagnetically. But, you know, if you're a binary star person, you absolutely know there's a ton of unknown physics, including about accretion, including just about how binary stellar evolution takes place and the formation channels of a lot of these very rare objects. So there is a ton of work that Lisa will help inform in this area. This is new, and it's one of those like smack your head kind of moments. As soon as LIGO found its first gravitational wave source, they were roughly 30 solar mass binary black holes, 30 solar masses each. And if you would have asked an electromagnetic astronomer, most of us, before LIGO observed, we would have said black holes are 10 solar masses. We know this because Cygnus X1 is 8 solar masses, and therefore they're all going to be 10 solar masses. But yet we found a 30 solar mass black hole, and they were a dime a dozen apparently. And so the neat thing about this is that in LIGO, we observe the merger. But if you dial back time and let these black holes, you know, exist for a couple years before merger, they're going to be orbiting at low enough frequencies, long enough orbital periods that they will, some of them, be observable with LISA. Now, again, this is an older figure, but you know, like basically the next day, somebody said, "Oh my gosh, you can see this with LISA," and yes, you can. So we can probe this absolutely new population to figure out, you know, how they formed, what their rates are, etc. Oh yeah, duh. And the neat thing is, if you have a 10-year heads up that roundabout there's going to be a merger of two 37 solar mass black holes with a spin of blah, 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 then you can follow up with a ground-based observation and, you know, extend what you know about the physics. Okay, there are other cool sources in LISA, and these are noted by these little tracks right here. Those are called EMRIs, extreme mass ratio inspirals. And what they are little neutron stars, white dwarfs, or little black holes, stellar mass black holes, orbiting around a supermassive black hole. And they're pretty darn cool. I did not warn you that that was going to happen. So what I'm going to play is, they're pretty darn cool because it takes a very long time for them to, for a little black hole to merge in with a larger black hole. And along the way, the small black hole exhibits a very complex orbit in around the supermassive black hole. And so you get a probe basically everywhere of what space-time looks like around that black hole. So you get tons of orbits, really loud, and an exquisite map of the space-time around a supermassive black hole, not just in the equatorial plane. And that allows you to constrain GR. So I'm just going to play a tiny little bit of this because it's super awesome simulation. So this is a black hole. This is the orbit that marks the angular momentum orbit of this small little black hole, and you can see the kind of complex orbital structure of an EMRI source. And you know, this is in a vacuum solution, but if there's a little bit of matter like dark matter or whatever that is also around this black hole, the EMRI will be affected. And so this is a great way to not only probe space-time and deviations from GR, but also whether or not there is extra matter around the black hole. Okay, I'm going to stop that, but if you continue watching that, you'll see cool resonances. Every so often, you'll get into a practically closed orbit, and pretty neat. Okay, you can also do cosmology with LISA in a couple different ways. One of which is using a black hole merger as a standard siren, or those of us who are in electromagnetic astronomy know standard candles. These are standard sirens. From the gravitational waveform, you can get that the mass of the system, the change in the frequency gives the individual masses of the black holes, let's say, and then the amplitude gives you the distance. And remember, I'm not talking about redshift, I'm talking about distance. And so if you actually have a contemporaneous electromagnetic signal from a merger, then you can get the redshift. And so therefore you can construct your Hubble diagram of of a bunch of different classes of black hole mergers. So for example, close by, you'll get these LIGO-like stellar mass black holes. You'll get MREs sort of at the middle distance, and the supermassive black holes at very large distances. And notice you're probing up to the region where there starts to be this, well, there's a tension between local measurements of H0 and high redshift measurements of H0, and we're able to probe regions that are currently unprobable. And some folks think even you don't. I hope everybody's okay. I hope that wasn't like a fire alarm or something.
You're okay. I don't know what that was.
Yeah. Okay. So my kids are fighting in the distance. I hope you're not hearing that. So it's that kind of, we're all in this together thing. All right. So instead of individual sources, you can also do cosmology with sort of a background of stochastic sources like cosmic strings or whatever that are individually unresolved. And I don't do this, but let's just say that signature here encodes things like the merger rate of that type of source, its energy emission, and here, this is the important part, the volume of the universe that it probes as a function of cosmological parameters. So if you know or can estimate this, you measure this, you have some guess of what that is as well. Again, I don't do this, but here are different types of inflation scenarios and the gravitational wave stochastic background that folks think that will be. Sorry, I can't think of the rest of the sentence. And here's the Lisa sensitivity curve. And so you can see, for certain types of inflationary scenarios or certain types of phase transitions during inflation, you can get a signature that would be observable with Lisa. But the best part for me is all the unknowns. So come on, every single time we open up a window to the universe, sorry, I know that that's a trite phrase now, but every single time you open up a new electromagnetic wave band, we completely revolutionize our view of the universe. And that's gonna be the same thing with Lisa. So as soon as Lisa turns on, something that we thought we knew is going to be totally wrong, and that's going to be extremely exciting. So there is a huge discovery space with Lisa, and I cannot wait. So now I'll ask you all, remember, what makes a gravitational wave is just matter moving. And so think about what the astrophysics you can do if you knew individual masses of things that are moving on timescales of minutes to hours, something that's changing like that. If you knew the masses to within 1%, if you knew the distances accurately, if you knew the spins and spin directions well, if you knew the eccentricity of the orbit, which is super hard to get really well. The sky localization, not so great, but better than LIGO. And some folks will talk about why a little bit later. So imagine what science you could do in your area if you knew this type of information. Because I will tell you, this field is very small, and we need help from astronomers who think about science in this way and what you could do with this extra information. So I'm going to leave you with this. Lisa is really happening. It's going to fly, we think, in 2034. It's a joint ESA-NASA mission. And now is a perfect time to think about how we can get the most science out of the data, because this is a brand new field and we need all hands on deck. So we would love y'all to work with us. So I'm going to end there and take questions. Thank you.
Amazing. So I don't know if everybody wants to turn off their or turn on their video for a second and clap their hands, or if you all want to just clap your appreciation. We're shouting out our love for you and appreciation. Thank you so much, Kelly. We did have some questions pop up in the chat while you were talking, and so I'm just going to take moderator's privilege here and read out some of them. Some of them are going to require you to be really mathy on the fly. So you can just say, no way, forget it. How about on the Slack? So the first question here comes from Louis Longo and says, quantum fluctuations in the early universe spread in all frequencies due to a lack of modeling, or is this a strong prediction? And he's asking this based on your slide for different detectors in the range of different frequencies.
Totally, woohoo! So it's not actual numbers. Yay, I can get this. Okay, so I'm also going to tell you some wrong things, but the way I think about it is, for example, for models that have that give you this background from cosmic strings wobbling or from them colliding, you get a really sharp burst in time in the time domain. So if you Fourier transform that into the frequency domain, man, you get a power at all frequencies. So it's that kind of thing. You're getting a fast kind of response that when you Fourier transform, it spreads out. So it's not a lack of modeling. It's actually what I mean, if we think cosmic strings actually do that kind of thing, then it's it's appropriate. Does that make sense? Hopefully that makes sense.
I think so. Please, if folks have a follow-up to their question, do not be shy to put it in our Q&A. We really like the interaction. We had a question about how many galaxies are at a redshift of 3, but that question has apparently been answered to great satisfaction. So Jack Sankey is pleased. Ilber Bautista Chivata asks, how likely would it be that LISA will see gravitational waves from different sources hitting the detector at the same time? This since there will be gravitational wave signals lasting for long times. And I think there was some discussion amongst others members of the SOC about this too, but it'd be great if everybody could hear the answer to sort of superposition of signals and how we handle that for LISA.
Sure. So the short answer is yes, absolutely. Remember, I was talking about this hum of 10 to the 7 individual close white dwarf binaries that are coming from all directions in the galaxy. So yes, absolutely, there will be several signals happening at the same time from different directions. And part of what I understand about the data analysis challenge right now is being able to disentangle the signals that are happening contemporaneously. And so some folks think that the best way to tackle this is not to try and subtract individual sources, but instead to kind of model in a Gestalt way the entire gravitational wave sky, and in a Bayesian way try and figure out, hey, this picture that we've got here is 10 to the 7 white dwarf binaries with X of them that are observable, resolvable, etc. So hopefully that helped a little bit, but absolutely yes, there will be signals that will happen at the same time.
Awesome, thank you. So Louis has another question for us and asks, do we know how many of the supermassive black holes that are observed have masses orbiting them, similar to the stars that we see around Sagittarius A star?
No, we don't know at all. And I tell you what, if you are not ready to jump specifically into LISA, but if you want to contribute to LISA science, your job, should you choose to accept it, is to help characterize the binary fraction of black holes and their separation distribution, their mass distribution. We have not seen any confirmed binary black hole in this mass range that is close enough to be emitting gravitational waves. There are some great candidates, but none of which that we would hang our hat on and say, that one we're going to totally see. That's not to say they don't exist. It's just an incredibly hard observational problem. And so we need help. Please let's help us.
Okay, and so just a little brief divergence here for media and culture. You mentioned black holes as a mosh pit, but you were also the featured interviewee by Dennis Overby on the New York Times. Do you really think that's what we should call them, Kelly?
No, absolutely not. So I have to credit Tex Stebbins' daughter, who decided to pose this question, and we decided to run with it and got sillier and sillier. So I don't really know what we should call them. I always call them a swarm, but I don't know what will happen.
For anybody that wants to see, there's an amazing Twitter. I should put the Twitter feed, but it's somewhere just like people throwing out a bazillion different ideas for what you call a collection of black holes. It's quite funny. All right, Jonathan asks, or I guess Jonathan is answering this question about multiple overlapping signals being detected. So we've got that here too. Let me see, I'm scrolling and scrolling. Richard Garnett asks, does the same power distribution among frequency occur with black hole binary mergers? And does this frequency spread give us information about what's happening within the merger inside of the event horizon at all?
I don't know about inside the event horizon at all, but I mean, I personally don't know in any way whatsoever. That's not what I mean at all. But what I can tell you is, yes, there's a spread in frequency. The little picture there. So this little track here comes from the fact that you get the black hole visits a bunch of different regions of frequency space. So that track is indicative of things like the spin orbit coupling, things like the eccentricity, certainly the masses and mass ratios. But I don't know anything about, if there is information, I'm going to go out on a limb here. If there is information about the event horizon, that would be inside the event horizon, that may well be encoded in the ring down phase, which I'm going to stop talking because that's about all I think I can safely say.
Okay, fair enough. I'm going to shift over to our Slack for a second, just to give Slack some love. Il-Seng Yoon asks, the multi-frequency gravitational wave observation probes the time evolution of the sources, which is very interesting, but also requires careful coordination between LISA and high-frequency ground-based gravitational wave experiments. Mm-hmm. What challenges will we have in that coordination avenue?
Well, the challenge for any coordination, I would say, is communication. But I think by then there will be enough interest so that we will have shaken out the communication route. Right now, for things in the electromagnetic regime, there are these astronomer telegrams, ATELs. So that is one way to try and spread the word about things that may be targets of opportunities for other observatories. I imagine there will be in the future these memorandums of understanding between a space-based instrument and a ground-based instrument, whether they be electromagnetic or gravitational. But that's above my pay grade. I would expect that to happen in the future.
Yeah, I can say for my part that it's very challenging, but I agree completely about the communication being really just absolutely crucial. And it sounds sort of trite to say that, but I think it's totally correct. So I will please, for everyone on this call, and we have callers from everywhere, and I will almost certainly mispronounce some of your names, so please just forgive me in advance. Panagiotis Isof, or Iosif, maybe a naive question. When LISA actually flies and starts doing science, would it be in danger from space debris, flybys, and things that could smash into it and damage it?
Yes, it could. But so in fact, so this was a huge worry of folks who thought, oh man, LISA's never going to be able to be technologically feasible, because there's space weather, just solar flares that are going to push on the telescope using solar pressure, also space debris, etc. So there's a bunch of junk in the universe that may well jostle the test mass, and you'll hear a little bit more about this in a little bit, and give you a fake signal of a gravitational wave when really it's just junk causing the test mass to perturb. But the humanity have flown this concept instrument called LISA Pathfinder, whose sole purpose was to say, how still can I hold this test mass given space weather, charges inside the the instrument flipping out, etc. And so far humanity has shown that we can keep the instrument far more still than what we thought. So apparently there's technology that can solve for that. But like if there were a meteorite hitting one of the constellations, then we're in trouble. But happily, there are 3 instruments. So folks are talking about how to carry on with just fewer links because yeah.
Super, thank you. I'll also follow up that Aaron Tovahahu, sorry, Aaron, points out that we're building a lot of really fantastic infrastructure in terms of software and data streams to help support the coordination of different observatories to do this gravitational wave science too. So that's already well underway and under development. And Aaron, for anybody who's curious, can ask him more questions about that on the Slack too. He's very knowledgeable in that area. So Louis follows up and says he's wondering, as a follow-up question about the candidates and events and merging with this question about overlapping signals, coming back to that. How come then we expect several of them to overlap? I understand that the duration of the overlap may be long, but what is the expectation about the number of overlapping events? And he's sort of noticing that maybe this is unknown, but maybe we have some expectations of thousands of these different signals being overlapping. How well constrained is that superposition? Okay.
Perfect. I think, so I am not the world's expert on this, but there are people in the audience who are. And here's what I can tell you in a very basic way. So the close white dwarf binaries that we're talking about, they will last for millions of years. They're called monochromatic sources. And given the frequency binning that we have, the frequency resolution that we have, and the fact that there's 10 to the 7 of them, it's inevitable that there's going to be, one here and one here that are orbiting at the same frequency, just in different directions, and they're lasting forever. How many? I don't know, but I think it is, so I'm gonna make up something. I think that there can be hundreds in the confusion limit, but I don't know for sure. And some of the things that will break that is that even in that frequency bin, if there's a really, if there's a bunch of them, but one's really loud, you can definitely resolve that particular one, even though there's a bunch in that frequency bin.
That's fantastic. All right, we have to wrap up. If people have questions, there's an H0 question here on the Q&A. So please shift those over to Slack. Kelly will hopefully join us, and other members of the community can also chime in and help do Q&A. So one more, just incredibly huge. I'm clapping for everyone. Kelly, thank you so very much for this great talk. If people have appreciation they want to share, please toss it in the chat too. Really a pleasure, and thank you very much.